in this class because it was too many things that weren't animated right. Well, I didn't add right on certain things. Just dumb human error kind of mistakes. But I think that's it. We are reviewing for the gas law test. I went ahead and well, it was Ms. Castleberry that did it. We sort of smushed kinetic theory in with this review instead of trying to do it as a separate day because it just wasn't that much. So, and we do plan on letting you use the review on your test. So, do it tomorrow. I thought you guys were doing English 2 tests. Oh, is yours tennis?
Yeah, I'm in tennis.
You're tennis? You're not going to be here for what?
English 2.
English 2 is Thursday. English 1, most of you should have been okay with English 1. Yeah.
For Thursday?
That's weird. That's weird. I don't know why. All right, so this kinetic theory of gases, what do we know about the motion of a gas? Just in general, oxygen gas, carbon dioxide gas, nitrogen gas, chlorine gas, carbon dioxide, carbon monoxide. What do we know about the motion of a gas? How does it move? You're right, move. Randomly. Okay, so it's going to randomly move around. Okay, they don't follow each other like little puppies. Let's see, there's Marisol. What else do you know about a gas? What about its volume and its shape? Okay, so if it's in a container, whether it be a balloon or like a hard can, it's going to take the shape and volume of its container because they do not have a definite volume or a definite shape. Why is this here? Oh, this would have been the bottom of the part. Did not need to get that. So we've got no definite shape or volume, but it will take the shape and volume of its container and fill it. And we've got random motion. Let's see here. Really, the gas laws do everything else. So, like I said, and it looks like it's frozen, and I didn't push the button, or I did, and forgot to unpush it. We're going to identify each one of these variables, these units, wrong word, as either volume, temperature, pressure, or moles. Okay, if you do not know your units, that's probably problem number 1 for pulling information out of the paragraph. So ATM is short for atmosphere. Atmosphere. Which of these is atmosphere? Which of those is it? It's pressure. Okay, C is Celsius. That's temp. We can't do these in Celsius. We have to change them to Kelvin using this. What about torr? It's pressure. Milliliters. That's volume. And then N. That's moles. Okay, so sometimes they actually just give you the number of moles. If they give you a mass for the gas, you would divide it by its molar mass, which changes it to moles, but I didn't see any of those on the test. It's just straightforward. But you need to make sure you are not in Celsius. So if you see the C, you need to keep adding 273 to change it to Kelvin because these do not work in Celsius. What about millimeters of mercury? That's pressure. Yeah, somebody decided to turn it up to 78 in one of my classes, that's why. Now, if you are at standard, it'll take on a second. So these, when you're at standard temperature and pressure, which I gave you on the paper, they both get 760. This one gets 1. And I haven't gotten the kPAs yet. What about Kelvin? Temperature. It's already in Kelvin. You don't need to change it into Kelvin. To get it back to Celsius, you would subtract 273. What about kilopascals? It's pressure. What about liters? That's volume. Now, not this one, but the other ones, it is okay if you're in milliliters or liters as long as they match. It's okay if you're in any of the pressures as long as they match, but you'd have to be in Kelvin. With this guy, you have to be in atmospheres, you have to be in liters, you obviously have to be in Kelvin to be able to use that constant. I'm going to fill this in. Which of these is, here, let me erase the rearranged part. Which of these is Boyle's law? Oh, it's Dalton's first? I apologize. Dalton's on the top. Which one of these is Dalton's law? Yeah, all the P's. So your total pressure, I just put TOT for short. I know it's small. It's as big as I could make it to fit in the space. Your total pressure is equal to the sums of your individual partial pressures. If you have 2 of them, you only need to add 2. If you've got 6 of them, you need to add all 6. But their sum is the total pressure. You're either adding or subtracting depending on what they provide. Now Boyle's law. Which one of these is Boyle's law? This one. Now, this is what is called an inverse relationship. It's an inverse. So if pressure goes up, what did the volume do? It went down because they do opposites. When they're linear, they're inverses. When they're proportions, it's not this guy, ignore that guy. When they're proportions, they're direct. So which of these two is Charles' law? It's V1 over T1 equals V2 over T2. The way that Ms. Youngman says it is if you have a boil, I know it's not spelled B-O-Y-L-E, but if you have a boil, you have large volumes of pus and intense pressure. And the way that she had them memorize the V over T is, this is Charles' law. Charlie Brown is on TV. It's the way she does it. And then for Gay-Lussac's law, which is this one, oh, well, okay, crap. Direct relationship. If temperature goes up, the volume will go up. If temperature goes down, the volume will down. And then Gay-Lussac's law, which is the one that's left over, is guys like power tools. But Boyle's does not have temperature, Charles does not have pressure, and Gay-Lussac's does not have volume. But this one, this is also directly related. If pressure goes up, what is temperature going to do? No, it's going to do the same thing. It's going to go up. When you combine them together, you get the combined gas law. I really should have put parentheses around the P and V's, but it wouldn't have fit in the space. I would have had to have made it smaller. So if you need to write it this way, you can write it this way. P1 V1 over T1 equals P2 V2 over T2. Where as long as the pressure matches, it does not matter which pressure. As long as the volume matches, it does not matter which volume, but the temperature's got to be equivalent. And then obviously the one that's left over is the ideal gas law. This is the one that brings in the number of moles. I know you're still writing some of these down. Are there questions about why they were direct or inverse? I need to take official attendance in here. That would be a wise thing to do. Where's my attendance paper? Here it is. So there's all. Really, I think these are yours. And you weren't here for a week. And that was on the floor from Wednesday. Since I take them as a test grade. All right, next one then. An ideal gas is made up of gas particles that do what? And then you guys have an A, B, C, D under it. Okay, so what you do on your paper, yes, you do too. So it says an ideal gas is a theoretical gas that has all the properties listed above. These properties are gases are composed of individual particles. Lovely, that's not listed here. Distances between gas particles are far apart. Okay, the gas particles are in continuous random line motion. It just means they go every which way all at the same time. Energy is transferred from one gas particle to another when they collide. Particles gas have no attraction to one another. Individual gas particles have no volume but do have mass. What is the only one that's listed up here that's right? They have random motion because they technically do not have a specific volume. So that's why this one's wrong. They do not attract each other. They bounce off of each other. So that's not right. They do too have a mass. Y'all, if gas did not have a mass, we'd all be dead right now. Okay? But they do have random motion. So the one that you need to circle that's correct is letter D. It's the only one that's written right. Now, if the gas is contained, then it's going to have a specific volume. But if it's not contained, it's just going to spread out until it can't spread out anymore. But they have to have mass, or we'd all be suffocating. We'd be in a vacuum, and we'd be trying to suck everything that's inside our bodies out to fill the void, and we would die. It's hot. All right, the next ABCD. The kinetic molecular theory that the particles okay, that's not grammatically correct. But anyways, we want to know that they are in constant random motion, that they're arranged in a regular geometric pattern, they have strong attractive forces between them, or they have collision that results in the system losing energy. Once again, there's only one that's right. Which one is it? You're right. It is either A, B, C, or D, which is the correct thing about the kinetic molecular theory. It's this one again. Okay, now, y'all, if it's in a regular geometric pattern, that's a solid. Okay, these are talking about gases, which is why this is not right. They are not attracted to each other. They don't group up. They go every which way all at once. And they don't lose energy. They are elastic. They're completely elastic. That means when they hit another particle, the energy is conserved. It's not lost. So it's the same as the previous one. Third one. I don't think this is an ABCD. Heating a contained gas at a constant volume will do what to the pressure? All right, so we have the aerosol can that we think is empty, and we throw it in the fire, which we don't do in real life. You heat that contained gas that is at regular standard pressure. What's going to happen in the can? It will eventually boom, okay, but before it booms, what's happening? It makes it boom. The gas inside, the temperature's doing what to the particles? Making them bounce faster. So if they can't expand, they're bouncing faster, what's happening to the pressure? It's getting bigger, and then eventually when the can can't hold it back anymore, and then it does what? Then it explodes. So the first thing is the temperature directly increases the kinetic energy, makes them move faster. They collide more often, including with the container. It causes friction. It pushes on the wall of the container, which increases the pressure. Yeah, if you don't get it out and it gets hot enough, that can is going to explode. And if you're in the wrong place at the wrong time, it'll shoot shrapnel straight through your body and can kill you, which is why we don't throw cans in the fire. It's also why you're supposed to keep certain things out of the trash. Nobody pays attention to it anymore. No, I'm not talking about me. It's like when we did hurricane pickup, you're supposed to keep your paint cans like separate. They're toxic things, and like nobody did it. They were throwing all their crap in a giant pile. Both. You have to treat like the actual paint, like when you pull the lid off, you're supposed to treat it with something before it gets thrown away. It has to be disposed of properly. Some paint, it just has to do with what's in the paint. Is it oil-based paint? Is it a latex-based paint? They're bad. They're rough. And sometimes you have to use oil-based paint, depending on what you're trying to get over. All right, so next one. Now we're getting into problems. About half the test is math and about half the test is vocabulary. We have a gas mixture that has oxygen, nitrogen, and carbon dioxide. That's awesome. Let's go to the important stuff. The total pressure is 250 millimeters of mercury. That's this. Now, I'm going to call the oxygen P1. So P1 is going to be 50. I'm going to call the nitrogen P2. P2 is 175. And I do not know carbon dioxide. I'm going to call that P3. So they need to add up to 250. I'm just calling oxygen P1, that's 50. I'm gonna call the nitrogen P2, that's 175. This was a typo, I had put 174, my finger just hit the wrong number and I didn't catch it till 4th, which is why I'm recording now and it's not already up in Canvas. So I know 250 equals 50 plus 175 plus X. So what do you do?
Substitute. Add the 50 and 75 and subtract the 50.
This. You can add, like you said, the 50 and the 75 and then subtract that from 250. Yes, you gotta go to A hole. It's still open. So 50 plus 175 is 225. What's 250 minus 225? 250 minus 250 minus 25. 25. So your third pressure, which is carbon dioxide, would have to be 25 millimeters of mercury. You're going to have one very similar to this, where you're not just adding them all up, you're figuring out what the missing partial is. Well, when we're through, I don't know, 4th period went to the bell because I had to keep fixing all my typos, all my fat finger stuff that I was doing. So I accidentally did 174 instead of 175. It was just wasn't looking at what I was typing. And we have another one. We've got a pressure of 2.5 atmospheres at 25 Celsius. Yes, I need to add 273. I'm going to call those my ones. Oh, what units are given? Temperature, volume, pressure are only some of them. We are only looking at pressure and temperature. So that means I have to use this one. But my first pressure is 2.5. It goes with the first temperature. I need to add 273. Well, if you're showing me your work and you're showing me work in Celsius and not Kelvin, I've been marking it wrong. Just add 273 to the C's and it changes it to K's. Then I know my new temperature, but I don't need my new pressure. So these are going to match. I need to add 273. And once again, I have to use Gay-Lussac's law to be able to solve the problem. Because that's the only one that talks about pressure and temperature and ignores volume. Because there is no volume on this problem. Sometimes it'll just leave it out, and sometimes it'll say the volume's constant. All I get to do is plug it in. So I'm going to put into this formula the 2.5 over the 298. I do not know P2, and I'm putting that over 523. I didn't rewrite the formula. This is substitution. How do you solve in a proportion? Cross multiply and divide, the poor thing left alone. So these are times each other, and this is in the denominator. I just made it linear instead of top and bottom because it's much faster for me to type it into the slides like this. When you put this in the calculator, it's going to give you 4.4 atmospheres. I just rounded it to sig figs. Now, I do not think my calculations are wrong. I was catching errors in my notes in 4th period on every single slide, sometimes more than one thing on a slide. So what happens when you have Easter weekend and you're trying to build stuff and you have 0 time to get it done. So yeah, I made lots of mistakes on this one today. Thank you, Carmel. Like I said, you can use this on the test tomorrow. The problems are not exactly the same, but there's one of each. Do not forget to change it to Kelvin. Let's see, who else am I missing? I'm missing, we got Wyatt, Tucker, Denson, Abigail, Jessica, Asher, Hayden, Daniel's not here. What's else on Nathaniel? Or did he go to the back? That was you. Okay. Wednesday? Definitely only Thursday and Friday. I wonder if I'm not the wrong person absent. Is it Nathaniel? Hold on, I'll go in and I'll look at it. Not really, Grayson, Kyle. Wow, you've been gone for a solid week. That is not good. Let me sample this and I'll take a look at it when we get into it. All right, next one. 5 liters of air at negative 50 degrees Celsius or warm to 100 degrees Celsius. We want to know the new volume if the pressure remains constant. My units that are present are volume and temperature. That's going to be this one. So these are my ones. I need to add 273. This is my 2. I need to add 273, and I am solving for V2, which is going to have the same unit. It's going to be in liters. And this is another proportion. How am I going to get you all this stuff? You're missing like all of the gas laws. No, you're missing combined, ideal. You're missing, this is ideal. This is combined. Here's the combined. So we did this, we did a work day, we did ideal, and then there's the Google slides that are in Canvas, which I think are good. This is good. Okay, all right, so we're going to use that proportion. We know that we have to use Charles' law, which is V1 over T1 is V2 over T2, because that's the one that's missing pressure. And I'm going to plug everybody in. 5 over 273 equals we do not know over 373. Decimal's there to try to drive significant digits. That's all. So we're going to cross multiply and divide by the thing that's left alone. So it should be 5 times 373 divided by 223. It's going to end up being in matching units, which is liters. Like I said, if they're both in milliliters, don't worry about it. It's this one that they can't be. They have to be in liters. If you put this in the calculator, right? And I round it to 6 figs, I get 8.36 liters, and I hope to God it did not smash buttons on the calculator wrong. All right, double check itself. Double check and make sure I didn't get a doo-doo because I was full of them this morning. 373 divided by 223. I get 8.363287. So I just rounded it to 6 to cut all the extra crap off. The next one, keeping up with this, we're on this one. Are there any questions on this one? Baby laws are easy. Oh, well, I reanimated Charles' law. That's lovely. All right, so this is what we did on Monday of last week. So this is where you started missing. Well, we have a 350 liter gas sample at 20 degrees Celsius and a pressure of 650 millimeters of mercury. I have V1, T1, and P1. The thing's allowed to expand to a new volume with a specific pressure, and we want to know the temperature that goes with it. So we're solving for T2. I have to use the one that smashes all three together, which is called the combined gas law, because I need all 3 units. I know this is sort of close right here. I probably could have tabbed it over one more, but I didn't do it. But your first volume is 3.5 liters. Your first temperature, add 273, which is 293 K. My first pressure, I just took the decimal off from sig figs, 650 millimeters of mercury. My second volume, it said, was 8.25 liters. I'm solving for the second temperature, which will be in Kelvin. But my second pressure dropped to 425 millimeters of mercury. Once again, these could have been in milliliters as long as they matched. This could have been in any of the 4 pressure units as long as they matched. I'm going to use the combined gas law, which is this guy. P1 times V1 over T1 equals P2 times V2 over T2. Which is technically also a proportion. We're just used to doing it with only 4 bits and not 6 bits. Because you're having a hard time solving for something in the denominator. Your brain's like, I can't do it, it's too hard. Yes, you can. I want to solve for this. I'm going to cross multiply and divide by the things that do not have all 3. Just like the other ones. So these are diagonal, they're going to go in the numerator, and I'm going to divide them by the 2 that are left out. If you're putting everything in the calculator at once, you need to put parentheses around the denominator, or the calculator ain't going to do what you want it to. It's going to do what you told it to. Or you could multiply at the top, right down, multiply at the bottom, right down. Do top divided by bottom, but don't round. Or you can just use parentheses properly in the calculator, stick your phone sideways, and it gives you the parentheses back. If you do this right, so you didn't make a mistake. This is something else I made a mistake on. So 425 times 8.25 times 293 divided by 650 divided again by 3.50, 451.5, so yes, 452 Kelvin, and I round it to 100. So Kyle, what you missed was like, it was the same stuff, it just smushed them.
Yeah.
That's all, it's why it's called combined. And you can still cross multiply and divide by things that are left out. So that I don't think you're gonna have an issue with. Just make sure you're in Kelvin. Make sure that your stuff matches. These match. And these match. As long as those match, then as long as you're in Kelvin, you're fine. Now the other one that you missed, which was Wednesday, Tuesday was a work day, not any paper. Okay, so you're sort of lucked out without having to do too much. So what pressure will be exerted by a 0.450 moles? That is the letter N of a gas at 55 Celsius. I need to add 273. It is contained in a vessel whose volume is 6.5 liters, which is my V. Okay, now this formula, now I know this is going to be my R because I'm in atmospheres. And I'm solving for pressure, it's going to be in atmospheres because you have to be atmospheres, liters to make this match, and that has to be Kelvin. Otherwise, I have to teach you all 4 rate constants, and I'm not going to do that.
Why?
You want to memorize more stuff?
I don't
Okay.
memorize it.
Okay. The rate constant when you're in atmospheres is 0.0821. I just cut off the unit because it's like this long, and I don't want to do that. This is equal PV equals nRT. You have to be able to rearrange to solve for variables. I actually just erased them from up here. I think I did it in this class. To solve for P, you're going to divide both sides by V. And you can substitute in first and then rearrange. It's just a lot more writing. I will have scratch paper up here for the test. It's half math and it's half vocab. So when I do, because I like to rearrange and then plug in, all I did was I divided both sides by the volume. Multiplied the other ones because they were already in the numerator. Hey man, you having tests tomorrow and you haven't shut up all freaking class. Hey Ness, you guys are driving me nuts. I swear it's not that hard if you guys just pay attention. So I'm going to do 0.45 times 0.0821 times, because it has to be in Kelvin, 328, divided by 6.5. It will be in atmospheres, and it's 1.86. Half of your test is math, half of your test is vocabulary. And this review pretty much does all of it for you. Obviously, it's not going to be these numbers. You may not be solving for pressure. If I asked you to solve for volume, you would divide both sides by P. I was asking you to solve for N, you would divide both sides by RT. I was asking you to solve for T, you would divide both sides by NR. But I'm not going to ask you to solve for R because it's always 0.0821. It's constant. Now, let me freeze this. Let me stop this. Stop recording. Okay, now